Okay, so we're going to continue our lecture. Today, we're first going to talk about the top 25 most dangerous software errors. The software errors has been classified into different categories. The first category is the insecure interaction between components. The first example is the circuit injection. Right? So this is a very common vulnerability in web applications. Okay, then there is a OS command injection, cross-site scripting. This is also web related. So number two often is related to the CGI, which is the server side of web. Okay. Then there is cross-site request forgery. So this is also a common web vulnerability. The number 9 is unrestricted upload of file with dangerous type. For example, if you have a FTP server which allow you to upload the exe files, okay, or if you have a web form, right? So if it allows upload of executables, those executables can be distributed to the other user. This can cause damage to their computers. Then there is open redirector. So the second category is the risky resource management. So the problem is like classic buffer overflows. We are going to talk about this in the lecture 2. Okay, so the basic idea is that if you have a buffer, for example, it can only put 8 bytes. But when you try to write into it, say 16 bytes, now you fill in the first 8 bytes, but you are also going to override whatever after the buffer. So this will overflow the buffer and override the memory after the buffer. So in computer security, if you can override 1 byte, even 1 byte, sometimes is sufficient to compromise the whole machine. Then there is a path traversal problem. So path traversal seems to be a simple problem, but think about it in the case of FTP server. Say you have a FTP server, right? You want to limit the path to be on the, say, VAR FTP root, right? You want to limit everything under this directory. But what if the attacker using this kind of path? Okay? So if you're not careful, so the dot is going to move the directory one level, another dot is going to move another level. Now you are at the root level on the etc. So the etc directory in Linux or Unix usually contains all the configuration files, so including, say, password database, right? So the download of code without integrity check. So in the early days, like for example, if you download, say, Firefox, okay, Firefox, it's going to give you a MD5, but this whole page is on the HTTP. Now, what is the problem? what's the potential security issue here? So of course, if you have a main in the middle, okay, so this is a Firefox server, or let's say Mozilla, right? So this is your personal computer. But what if in the between there is a attacker who can manipulate your pages? So the attacker can give you a hacked Firefox, right? At the same time, it's going to update the page to update the MD5. Okay. Now at your computer, right? So you get the file, but you also check the MD5. You don't know the MD5 has already been compromised. So now you get a compromised Firefox installed. Okay, so normally if you do this kind of thing, you should put this on the HTTPS, right? On the HTTPS, it's going to provide a strong protection. So of course, download the code without an integrity check is even worse, right? Inclusion of functionality from untrusted control sphere. Okay, so this is also common. Say, for example, in the web. So in the web, so the current web applications are actually extremely complicated. So a single web can take in tens, if it's not hundreds of libraries. Okay, so these libraries sometimes you cannot control their security. So I believe in the last year or the year before, there is one of the library is being compromised with the crypto miner. Okay, so it's basically mining the cryptocurrency. I mean, one of the library is compromised with the CRYPG crypto miner. Okay, now every website using this particular web library, right, is going to load this malicious library. So it's going to do the crypto mining on the visitor's browser. Okay, so one way to solve this problem, this on the untrusted library, so you can when you import a library into a web page, you can specify the hash of the library, right? So this will give you at least some protection. So use the potentially dangerous functions. There are a lot of dangerous functions, such as system, SYSTEM. So system is basically a C library function which will fork the current process and run the command. Okay, so it's basically a way to run a new command. So now if we have this parameter is the string of the command. Okay, so if you're not careful and this command can be untrusted or under the control of the attacker, they can execute any program on your computer. There is also incorrect calculation of buffer size. This is often say off by 1, kind of vulnerability, right? So this is commonly in the say in the C, a string is actually end with a 0. So if you didn't count the 0, you only count the how many bytes you have in the string. You are going to override 1 byte after the buffer with 0. As we mentioned, even 1 byte can sometimes is sufficient to compromise the whole computer. So uncontrolled format string, this is the format string vulnerability. Right? We're going to talk about this in the later lectures. And also the integer overflow, or sometimes we call it integer errors. Right? So all kinds of integer errors. Sometimes it's overflow, sometimes it's wrap around, or sometimes it's the signedness. Okay, whether it's positive or negative. So this is the second category, risky resource management. So there's also porous defenses. So for example, you have a missing authentication for the critical function, or use hard-coded credential. So this is actually very common in mobile applications. If you think about this, right? So if you have a mobile app, and it use say Amazon EC2 cloud to store files. Okay, so for the app to access the EC2 cloud, it needs to have a developer credential, right? It needs to have the password or the key to access the EC2 cloud. Now, where do you store this key? In the mobile app, right? Sometimes they just put the key. Sometimes they just put the key in plain text in the mobile app. Sometimes they encrypt it. But the best protection is to use the facility provided by Amazon. They have this this whole infrastructure built to just support this kind of application. Okay, missing encryption over sensitive data. So the sensitive data must be kept secret. Relies on untrusted inputs in security decisions. So use of a broken or risky cryptography or algorithm. Okay, so for crypto, so the number one rule of crypto is never reinvent the wheel. Okay, never reinvent the wheel, which is a very bad idea. Okay, so you should instead use the mature library. Use the mature library, right, to both the existing mature library and protocol. Okay, this is very important. Don't try to reinvent the wheels. So you should use the existing mature library and the protocol. There are a lot of crypto libraries, such as the Boring SL, right? So the OpenSSL. OpenSSL is very large. Then Google has its own flavor. It's called Boring SSL. Okay, there are a lot of other libraries as well. So remember, okay, never try to create your own encryption algorithm. Use the existing mature library and the protocol. Okay, until you are become an expert in the area of crypto, before you can do this. Okay, next let's talk about bugs. So just some quick rundown of some typical bugs. Like here, this is a buffer overflow problem. Okay, so look at this source code and see where is the problem. Okay, so if you look at this, right, let's define a buffer called a buffer over 8 bytes. Okay, now when you use get, it receives from stand input. Okay, when you do the get, so the get has no idea how many bytes the buffer has. So it's just going to receive whatever. It's just going to put whatever received from standard input into the buffer. Now, if the standard input is say 8 bytes, right? So this can be put in the buffer comfortably. So, but if the standard input is say 24 bytes, now you have extra 16 bytes, which will override the content because the buffer is on the stack, right? So it's going to override the stack, the stack. So if we draw the memory layout of this function, so for the main, right, we have the return address. So even though main is supposed to be the main function or the entry point of your program, but the main function is actually not the first function being called by operating system. So there is a return here, then it's going to allocate the buffer. Okay, this is 8 bytes. Okay, when you do the get, it will fill in. Okay, so the stack goes down. This is the high address. This is the low address. Right, stack goes down. So when you do the push, it's going to push to the bottom of the stack. Right, when you do the pop, it's going to pop from here. But when you write into the buffer, so because this is the low address, so it's going to write upwards. So this is the direction for write. This is the direction for the stack. So now, if we look at the buffer here, so you first fill in the buffer, then extra bytes is going to override the content after this on the stack. So this will including the return address. Now the attacker has control over the return address. It can point to a piece of malicious code. It's called the shell code. Okay, so when you return from the main function, it's going to pop a return address from the stack and execute the shell code. Okay, so we're going to talk about this in greater details later. Okay, so if you don't know much of this, don't worry. So we're going to provide more details. So the second vulnerability is integer overflow. Okay, so take a look. Where is the possibility of integer overflow? Okay, so if we look at this, packet get int. Let me change the color. Okay, so packet get int. So basically, you are taking an integer. from the packet, from network packet. So the network packet, usually it's considered to be untrusted. Okay, so it means that the NISP in response is untrusted, right? So it can be any value. So if NISP is larger than 0, okay, it's going to malloc the NISP multiplied by size of char star. So you are basically create an array of char star, right? So this is a char star, a pointer to string, a point to string. So with the NISP in response entries. Okay. However, if we look at this, right? So the NISP, let's assume this is on the 32-bit machine. Now the size of char star is how many bytes? It's 4 bytes, right? So you multiply this number by 4. Okay, so if the number NISP is larger than 2 to the power of 30, now the number is larger than 2 to the power of 32 when you multiply this by 4. Okay, it means that you are going to, when you do this, this is a bit 0, bit 31, and 32, but the 32 will be discarded. So you're actually going to get a very small number because this can overflow the 32-bit integer. Okay, so in the computer, right? So especially for programming language like C or C++, all the variables has its internal memory size. Okay, so normally on the 32-bit machine, it will be 32 bits for int, right? Okay, so if the result here cannot fit in 32 bits, it's going to cut off, right? So cut off the top bits and throw them away. Now you get a smaller integer. So this is the integer overflow. So here is another example. It's called integer error. Integer error. This is related to the sign of the integer. Okay, here. So this is actually somewhat similar, right? So you have a buffer. This is the buffer called strm. So then you have a buffer called BUF 512 bytes. Okay, so you are taking. So if you look at this piece of code, it's not the best practice to write it in this way. But what they want to do is basically you point to this, then interpret this as a short. So you basically take 2 bytes from strm and interpret it as a short integer. Okay, then you move the strm by adding to the size of a short integer. Now your strm actually points to here. Now your strm actually points to here, right? Okay, so if NAS is less than 512, you do the memory copy, buffer from buffer buffer is the destination. You're actually copying the content from strn into the buffer. Okay, so what's the problem here? Okay, so the problem is that when we have a short, right? This is a signed. Signed means that it can be positive or negative. Okay? It can be positive or negative. But so if length is negative, right? If length is less than 0, of course it's also less than 512. When you do the memory copy, so the memory copy, so this is the type of this third parameter is something called a size t. Is something called a size t. Okay, size t is unsigned integer. Now you are converting a signed number to the unsigned integer. Okay, so in the memory, a negative number is actually represented by its in this form. Okay, so the first say several bits are all ones, then you followed by this number. Okay. Now when you convert it to unsigned int, so the C language is not going to do the conversion, right? It's not going to throw an error. It's just give this memory to this parameter. Now suddenly this number becomes huge. It becomes larger than 2 GB actually. Okay, so you are converting a negative number to a positive number, which will become a very large positive number. Now you are copying so much data into the buffer. This is definitely going to overflow the buffer. Okay, so this is called an integer error or signedness error because length is first is signed, then it's being used as a sign. Okay. Okay, so this is the format string vulnerability. So the format string vulnerability is actually very easy to identify. So the format string is something we used in, say, printf. Right? When you do the printf, you first give it a format string. So for example, like %d, %s. Okay, so then you followed by integer, then a string, right? Now you are going to first print the integer, then you print the string. So this is called a format string. Okay, so if the format string is untrusted, now you get a format string vulnerability. So untrusted format string leads to format string vulnerability. Okay, so if you look at this, so the snprintf, so the first parameter is the buffer, second parameter is the buffer size, the third one will be the format string. Okay, in this case, it's the format string comes from the command line. Comes from the command line, the user input. So this is untrusted. Okay, when you have the command line, right? So sometimes, okay, let's not talk about this. Okay, the next one is a circle injection. Circle injection means that you have a SQL command. So like here, you select star from the user database where the username equals to the username variable, the untrusted input. Now the password equals to a password. It's also the untrusted input. Okay. So if you look at this, right? Hi, this is your son's school. We're having some computer trouble. Oh dear, did he broke something in a way? Did you really name your son Robot? Job table student? Okay. Okay, so if you look at this, right? If we put this into the into this query, so we get a user name. Let me change the color of the pen. We get a username equals to we have the first half of the quote robot. Then there is another quote in the input. Okay, so this will okay. So now this will end this query, and it's going to start a new query. Okay, so the job table student. Okay, then you have dash dash. If you look at this, right? If you look at this, so now you are selecting star from users where username equal to robot. Then you drop the table students. You have a second command, second query. It's going to the drop the student table, and also these two dash dash actually tells the command circle engine the rest of the input will be comments. The rest of the input will be comments. Okay. Right. So this is a typical example of SQL injection. So this is actually quite common. It's still one of the top vulnerability in the web, as we have just showed in the top 25 most dangerous vulnerabilities. Okay, of course, this is actually very easy to prevent, right? So most modern SQL engine actually provided something called a prepared procedure, which it basically tells the SQL engine which part is the user input, which part of the command is the command itself. Okay, so now with the prepared procedure, this part will be considered as the user input. It will never be interpreted as a part of the command. Okay, so this is another example, Sony PS3 Epic Fail. So game consoles, right? So the game console, the security of gaming console is actually a very hard problem. If you think about this, right? So your gaming console actually sits in your customer's home. So they can do So they have physical access. They have physical access to your hardware. So they can do whatever they want to your game console, right? So it's actually a very challenging problem because of this. So if you look at this, the PS3, it has like a chain of trust. So the chain of trust is we have briefly mentioned this. Okay, so the chain of trust basically means that you have created a chain of trust from boot to your system, right? So normally when you boot a machine, you have a CPU which will load the firmware, right? So the firmware will load the bootloader. Will load the bootloader. Okay, then the bootloader is going to load the operating system. Now it will load the games, right? So the chain of trust means that every piece of component, from firmware to bootloader to operating system to the games, are certified. Okay, so it comes from trusted source. Okay, of course, in many cases you don't want the firmware to load the operating system directly, right? So normally you have a bootloader, like in the Linux case, that would be the grub, right? So to load the operating system. Okay, so you don't want firmware to be too complex. Then it has put a console key, signed executable, as we have mentioned, right? If you have a chain of trust, every piece of component is actually signed. It has security coprocessors, encrypted storage. So it has a hypervisor, but the hypervisor here is for the security purpose. Okay, then it has user and kernel mode. Okay, so because those are specialized machines, so for other earlier consoles, they actually don't have a user and the kernel mode separation, right? So everything runs in the kernel mode for say x86 300 x86 for Xbox 360 or Wii, okay? But PS3 has this simple epic fail. So the get a random number, it returns a constant. Okay, so for encryption, in many cases, right? Encryption relies on high quality random numbers. Okay, if the random number is constant, it means that it's very easy to predict, or it's very easy to do the decryption. Okay, so it depends on high quality random number. So you cannot just say, okay, a random number can be any number, so a constant is as good as any number. But for the security purpose, you must have a high quality random number. So the high quality random number is actually very difficult to generate on the digital computers, right? So the digital computer is deterministic, but the random number is non-deterministic, right? So you don't want a random number to be deterministic. So for example, if you get a random number from the libc, libc has a number of random number functions. So those are called pseudo random number. Okay, it means they are fixed random number. They are predictable. If you know one number in a sequence, you know every single number after this, okay? And also every single number before this. It's called a pseudo-random number. To generate a true random number, you need to have a source of randomness. For example, in the Linux, okay, some source of randomness will be the current time, but the current time is actually has very limited entropy. So the entropy means how many bits of randomness you have, right? So the current time, so the time of say you receive a network packet, you receive an interrupt, right? And also when the user say move the mouse or type on the keyboard, right? So the user input. Okay, so there are a number of those events which interacts with the external environment can become the source of randomness. Okay, and also, so you can have a hardware random number generators. Okay, almost every platform has this hardware random number generators. Of course, you don't want to trust the hardware random number generator alone, right? So you want to just in case those small chipset are being compromised or being planted with flaws. So you want to use this just a part of the randomness, but also mix in multiple sources of randomness. Okay, so again, never use a constant number for random number for security purpose. Okay, then this is actually very interesting, right? So the Apple go to fail. So this is the function is a SSL verification. So you verify signed server key exchange. So it's a part of the key exchange. So you're going to this function is going to verify this key exchange. So if you look at this, right, here is very suspicious thing. So if this error, then you need to go to fail, right? But there is if you look at this, right, there is a extra line of go to fail. Okay, it means that no matter what, right, it's going to go to fail. So let's look at the what happens if you have a certificate or key exchange process which passed those two checks. Okay, so if we didn't pass this check, right, we go to the fail and the error, it will return error message. Okay, if we look at this, if it passed this one, if it failed the second check, okay, it's going to go to fail and then return error. Okay, so when the program executed the if the program executed the second go to fail, so when it's being executed, ERR actually equals to 0. Now it's going to execute this piece and then return 0. 0 means the key exchange is valid. Okay, key exchange is okay. So now, if you look at this, right, because of this extra go to fail, so all those checks after this will be skipped. Okay, so this is why this is so this can cause a lot of security issues because all of those skipped validations verifications. Okay, so this is some there's some conspiracy theory involved in this go to fail vulnerability. Okay, so if you look at this, right, the intention of those two go to fails is actually not natural, right? So if you have any decent editor, it's going to move the go to fail here to be aligned with the if. That would be much easier for human to spot this problem. But because it's indented to another go to fail, it's easier to be missed. This is why there have been some conspiracy theory. So this was planted by somebody working for who knows who, right? Okay, so another high-profile vulnerability, OpenSSL Heartbleed. So the OpenSSL Heartbleed is a vulnerability in the OpenSSL library. So the OpenSSL library is actually used very widely. It's ubiquitous. Okay, so the Heartbleed, it's actually a problem in the heartbeat protocol. So the heartbeat protocol, right? So in the TCP, there is something similar called a keep alive. Okay, let's talk about the TCP, right? For TCP, you have a sender, you have a receiver, then you're going to create a TCP connection. So TCP connection can exist for a long time, right? But okay, if you have a firewall in between, right? Sometimes, so the firewall can drop the state, drop the connection. If there is no data flow on this connection, right? If there is no data flow on the connection for a long time, firewall is going to drop the connection. So now, so the TCP has something called keep alive. Every once in a while, it's going to send a small packet to the other side and tell every device along the way this connection is still alive. So this is the concept of keep alive. So the heartbeat protocol in OpenSSL is actually very similar in concept. Okay, so it's going to periodically send some message to the other side to tell the other side, I'm still alive, right? So the heartbeat message is actually very similar to the ping. The protocol is very similar to the ping. We know ping is something called a ICMP protocol, right? So you have a ICMP echo request, then you send a echo request packet. It's going to return a echo reply message. Okay, this is similar. So you send a heartbeat message, right? So that you have a length 4 bytes. Okay, so this is the heartbeat message. So the TSL1 heartbeat request. So the length, what's the length of this payload? Then you have the payload data. So the receive side is supposed to return a heartbeat response with the same length and the payload data. Okay, so normally if the server side say, okay, a reasonable server side say you only have 1 byte of payload, but you are asking for 64K of data to be returned, I will only return 1 byte. Or I'm going to return, say, 64 kilobyte of 1 byte followed by maybe zeros, right? But here, the OpenSSL heartbeat vulnerability, so the send side or the receive side is going to respond with 64 kilobyte of data. So if you look at this, right, so this is the request message this is the receiver side, right? Then this is the original request. So when it's going to reply, it's going to guess what happens. It's going to continue read from the request message and sending the 64 kilobyte of its own data over the receiver memory. It's going to send this to the sender or the requester. Okay, now every time the attacker say, give me 64 kilobyte of data, but I only provided you 1 byte, you're going to send 64 kilobyte of your own data to this guy, to the attacker, right? Okay, so if this happens so many times, it's going to get some sensitive data. In some case, it will be the, say, private key of your SSL certificate. Now you're going to lose everything. But the problem is that make it even worse. Okay, so this message is not being logged. So the server admin has no idea whether this happened or not. Okay, to make sure the security, normally they need to get a new certificate. Okay. Okay, so let's stop here.